So for this question, the objective in question is I understand I can use in calculations the requirements necessary for waves to constructively and destructively interfere. So in this question, we have the air and the soap bubble and then the air, and we have the two waves adding to it. So when it asks for the equation of the total phase difference between wave A and B, when they both exit the soap bubble, we see that wave A goes down through the air and then hits the soap and then comes back up. And since we know that the air has an n value of 1 and the soap has an n value of 1.42, we know that it bounces up exactly the same and there is no phase shift. However, when we go down here to the bottom of the soap bubble, it goes from soap to air, and that shift, because it's going from a higher n value to a lower n value, means that it will have a phase shift of plus pi. So in this instance, if we have our phase here, we get that k, in this case delta y, since they're going up and down, that's our distance, plus the phase shift. In this case is pi, so it's b minus a, which means we get a positive pi, because the a wave has a 0 in that case, so it would be pi minus 0. So we get kd plus pi for part A. And then for part B, we know we're looking for the distance d within the bubble, so here. And then what we do know already is the wavelength through the air that we can see. So we want the wavelength within the bubble. So we have 550 nanometers times that n value of 1 is equal to the wavelength within the bubble times 1.42, which is that n value in the soap, which gets us that the second wavelength within the soap is 387.3 nanometers. So we plug this into our original equation, where we know that the phase difference is equal to 2 pi m, since they add constructively, which is stated in the problem statement. Do a little math magic. We end up with 3.14, that's that pi, is equal to 162,000, nope, more than that, 16 million-ish, and then we end up solving for d and find that d is 1.94 times 10 to the negative 7th meters.